In this lecture, I am going to present what is symmetrical frames and analysis of symmetrical frames when the axis of symmetry passing through the midspan of beams. Then I would like to explain one problem when the axis of symmetry passing through the midspan of beam. First, coming to the what is symmetrical frame. When the geometry and loading applied on the frame are symmetrical, then the frame is known as symmetrical frame. In the case of symmetrical frame, there is no side sway occurs. Also, the bending moment in the frames would be symmetric. Therefore, take the advantage of symmetry, analyze only one half of the structure and express the values for the other half of the structure. There are two cases of symmetry arises. When the line of symmetry passing through the midspan of beams, this case occurs when the number of bases is odd. Then the second one, the line of symmetry passing through the column, which normally occurs when the number of bases is even. So in this lecture, we will discuss when the axis of symmetry passing through the midspan of beams. Look at the figure. This is the one base single story frame, and look at this figure. This is three base and single story frame. So here this is the center line. So here the center line which is passing through the midpoint of the beam AB, and here also the center line or axis which is passing through the midspan of the beam AB. When the frame is symmetrical, the rotation of midspan of beams through which the axis of symmetry passes is 0. Considering only half the frame with fixed ends are the midspan of beams through which the line of symmetry passes. Let AB be any horizontal member of a frame. Here the axis of symmetry passes through the center of AB. Let MAB and MBA be the end moments. Because of the moment MAB, the end rotated by theta A. Similarly, the moment MBA causes rotation theta B at B. Because of symmetry, theta A is equal to theta B. Therefore, the moment MAB and MBA are numerically equal but opposite sense. So, MAB is equal to minus MBA. The slope theta A at A is obtained by superposing the rotations due to MAB and MBA respectively. So here theta A is equal to theta A dash plus theta A double dash. Theta A is equal to theta A dash plus theta A double dash. Due to the moment MAB, the rotation takes place at A, this is theta A dash, and due to the moment minus MBA, the rotation takes place at A, this is theta A double dash. So theta A is equal to theta A dash plus theta A double dash. From the moment rotation relationship, we have theta A dash is equal to MAB L by 3EI and theta A double dash is equal to minus MBA L by 6EI. But we know MAB is equal to minus MBA, so put the value of MAB in this expression. So here MAB into L by 6EI. Then the rotation at A, that is theta A is equal to theta A dash plus theta A double dash. So theta A dash is equal to MAB L by 3EI plus MAB L by 6EI. So this is equal to MAB L by 2EI. Let this member be replaced by the member AB dash, whose end A will undergo rotation theta A due to moment MAB applied at end A and end B being restrained. The substitute member will have same value of I as the original member. Look at this figure. So here the end A is hinged and the end B dash is restrained, where the X is passing through the midpoint of the beam. So here you have to take the restrained end, this end is hinged, and due to this moment MAB, so this is the rotation takes place theta A, and the length of this substitute member is L dash, that is equal to L by 2. So for a typical substitute member with one of the end fixed, the moment and rotation relationship is theta A is equal to MAB into L dash by 4EI, where L dash is the length of the substitute member. So as you know, from this relation theta A is equal to MAB L by 2EI, and when the midpoint of the beam is fixed and another end is rotated through the moment MAB, so here the rotation theta A is equal to MAB L dash by 4EI. So equate these two equations, MAB L by 2EI is equal to MAB L dash by 4EI. After cancelling MAB 2E and this side MAB 2E, so the equation becomes L by I is equal to L dash by 2I. Then I by L is equal to 2I by L dash. So I by L, this is the relative stiffness of the original member. I by L is equal to K, and I by L dash is equal to K dash. So here K is equal to 2K dash. K is the relative stiffness of the original member, and K dash is the relative stiffness of the substitute member. K dash, this is the relative stiffness of the substitute member, is equal to the relative stiffness of the original member divided by 2. You can find out the relative stiffness of the substitute member K dash, that is equal to the relative stiffness of the original member divided by 2. So if K is the relative stiffness of the original member AB, then it can be replaced by a substitute member AB dash having the relative stiffness K by 2 with fixed end at midspan. With the replacement of a substitute member, the analysis should be carried out only for one half of the frame, considering the line of symmetry at the fixed end. Then coming to what are the step-by-step procedures follow for the analysis of symmetrical frame by Kanis method. So as you know, so the first step that you have to find out the fixed end moments by assuming the ends are restrained or fixed. So you have to find out what is the fixed end moment. Then you have to find out the relative stiffness of the members. Then you have to find out the relative stiffness of the joints. Then you have to find out the rotation factors in a tabular form. So you can find out the relative stiffness of the members, relative stiffness of the joints, and rotation factors. Then you have to determine the rotation moments by iterative process using this formula. This is the formula: m dash AB is equal to minus half KB divided by summation of KB into MFA plus summation of m dash BA, where m dash AB is the near end rotation moment and the summation of m dash BA is the sum of the far end rotation moment, and MFA, this is the fixed end moment of joint A, and KB, this is the relative stiffness of the member AB, and summation of KB, this is the relative stiffness of the joint A. So here m dash AB is equal to UAB into MFA plus summation of m dash BA. So UAB, this is the rotation factor. So this is equal to minus half into KB divided by summation of KB. So the rotation factor that you can find out by taking minus half into relative stiffness of the member divided by relative stiffness of the joint. After knowing this rotation factor, then you can find out what is the near end rotation moment. That is equal to the rotation factor into the fixed end moment of the joint plus the far end rotation moment. In first cycle, you have to assume the far end rotation moment that is equal to 0. If the end is fixed, also you have to take the far end rotation moment 0, and if the end is not fixed, and you have to assume the far end rotation moment that is equal to 0. Then in subsequent cycle, so you have to take what is the moment, the rotation moment you get from the first cycle. So that moment you have to take in the next cycle, in second cycle. Then you have to continue the iterative process. Again, after getting the rotation moment, then again you have to go for the third cycle, and what is the rotation moment you got from the second cycle, then that you have to use in the third cycle. So in this manner you have to find out what is the near end rotation moment of the end of the members. You stop the iteration process when the values of both the cycles are same. Then you have to take the last value, that is the rotation moments of the frame. Then after getting the rotation moment, then you can find out the final moments. The final moment MAB and MBA can be determined by the superposition of the three moments. So MAB is equal to MFAB plus twice into M dash AB plus M dash BA. So MFAB, this is the fixed end moment AB, and twice M dash AB. So this is the twice into the near end rotation moment, and M dash BA, this is once into the far end rotation moment. Similarly, the MBA can be determined. This is equal to MFBA plus twice into M dash BA plus M dash AB. So this is the fixed end moment of the member BA plus twice the near end rotation of the member BA plus once the far end rotation of the member AB, M dash AB. The moment M dash AB and M dash BA are called the rotation contribution, or this is also called the rotation moments. The final moment is equal to fixed end moment plus twice the rotation contribution of near end plus rotation contribution of far end. So this is the formula. By using this formula you can find out what is the final moment. Then coming to one example, analyze the frame as shown in figure, taking advantage of the symmetry of the frame and loading. So this is the one base two story frame, and this is A, B, C, D, E, F, and here on the horizontal member CD there is present the 20 kilonewton by meter uniform distributed load, and on the horizontal member B there is present two concentrated load of 30 kilonewton that is present at a distance 2 meter from the support B and from the support E. The span of the horizontal member is given 6 meter, and the height of the vertical member AB and BC, this is given 3 meter, and the moment of inertia of the vertical member is given I, and the moment of inertia of the horizontal member is given 4I. By taking the advantage of symmetry of the frame and loading, here you have to analyze the half of the portion of the frame. So here you take the substitute frame by taking line of axis which is passing through the midpoint of the beam here, and here you take as a fixed end, take the substitute frame and analyze the substitute frame. So this is the substitute frame. As you know, in the first step, so you have to find out the fixed end moment at the end of each members. Here you see on the horizontal member CD, so there is present the 20 kilonewton by meter UDL. Find out what is the fixed end moment MFCD and MFDC. MFCD, this is equal to minus 20 into 6 square by 12, and MFDC is equal to plus 20 into 6 square by 12. This is, so MFCD is equal to minus 60 kilonewton meter and MFDC plus 60 kilonewton meter. Then on the horizontal member B, there is present two concentrated load 30 kilonewton and 30 kilonewton at a distance 2 meter from the either end. So here you find out what is the fixed end moment MFB and MFEB. So MFB is equal to minus 30 into 2 into 4 square by 6 square minus 30 into 4 into 2 square by 6 square. this one. This is equal to minus 40 kilonewton meter. Similarly, find out MFEB. MFEB is equal to plus 30 into 2 square by 4 by 6 square plus 30 into 4 square into 2 by 6 square. So this is equal to plus 40 kilonewton meter. Then on the vertical member there is no horizontal loading. So here MFAB, MFBA is 0, MFBC, MFCB is 0, MFED, MFD is 0, and MFEF and MFFE 0. The fixed end moment on the vertical member, that is equal to 0. So this is the fixed end moments. Then as the axis is passing through the midpoint of the beam, so here you take the half of the beam and take the midpoint, that is the fixed end, and this is the substitute frame. Find out the relative stiffness and the rotation factor of the substitute frame. As you know, for the original frame, the relative stiffness of the member CD is equal to KCD. So this is equal to 4I by 6. And the relative stiffness of the original member B, that is KB, is equal to 4I by 6. But in substitute frame, when you take the fixed end at the midpoint of the beam, here you have to take the relative stiffness of the substitute frame. So the relative stiffness of the substitute frame, K dash is equal to K divided by 2. Here you can find out K dash CD is equal to KCD divided by 2. So this is equal to half into 4I by 6. This is equal to I by 3. Similarly, K dash B is equal to KB divided by 2 is equal to half into 4I by 6 is equal to I by 3. So this is the relative stiffness of the substitute frame. Then for the vertical member AB, the relative stiffness KBA is equal to I by 3, and for the vertical member BC, KBC is equal to I by 3. So these are the relative stiffness of the substitute frame. So here you find out what is the rotation factor of all the members in a tabular form. Here you draw the 5 vertical column, and the first column represent the joint, and second column represent member, third column represent relative stiffness of the member, and the fourth column, this is the relative stiffness of the joint, and the fifth column, this is the rotation factor. Here you see, so at joint B there are 3 members meet, BA, BE, BC, BA, BE dash and BC. So here you write BA, BC and BE. There are 3 members meet at joint B. Similarly at joint C, 2 members meet, CB and CD. CB and CD. So first you write in member BA, BC, BE, CB and CD. Then you find out the relative stiffness of the member. So for BA, the relative stiffness, this is the relative stiffness, the moment of inertia by length of the span. So the moment of inertia BA is given I, and the length of this vertical member is given 3. KBA is equal to I by 3. Similarly, KBC is equal to I by 3. Then KB is equal to 4I by 6, 2I by 3. Then you find out the relative stiffness of the substitute member K dash B is equal to KB by 2. So K dash B is equal to I by 3. This one, I by 3. Similarly, at joint C, 2 members CB and CD. So the relative stiffness of the member CB is equal to I by 3, and the CD is equal to 4I by 6 is equal to 2I by 3, and K dash CD is equal to I by 3. So these are the relative stiffness of the substitute members. Then find out the relative stiffness of the joints B and C. Find out what is the relative stiffness of the joint B. At joint B there are 3 members meeting. So BA, BE dash and BC. So here you take the relative stiffness of these 3 members. KB is equal to I by 3 plus I by 3 plus I by 3. So this is equal to I. Similarly at joint C there are 2 members meeting, CB and CD dash. So here you take the relative stiffness of the member CB and CD dash. The relative stiffness of the member CB is equal to I by 3, and the relative stiffness of the member CD dash is equal to I by 3. So KC is equal to 2I by 3. So this is the relative stiffness of the joint. Then find out the rotation factors. As you know, the rotation factor that you can find out by using this formula, minus half the relative stiffness of the member divided by the relative stiffness of the joint. So here you know the relative stiffness of the member, and this is the relative stiffness of the joint. So find out UBA, this is equal to minus half KBA divided by summation of KB. So KBA is equal to I by 3 and summation of KB is equal to I. So minus half into I by 3 divided by I. So this is equal to minus 1 by 6. Similarly, find out UBC, this is equal to minus half KBC divided by summation of KB. So this value is minus 1 by 6. Then UBE, so this is equal to minus half KB divided by summation of KB, and this value is minus 1 by 6. Similarly, find out UCB is equal to minus half KCB divided by KC, and this is equal to minus half I by 3 divided by 2I by 3. So this is equal to minus 1 by 4. Then find out UCD, this is equal to minus half KCD divided by summation of KC. So here KCD is I by 3 and KC is equal to 2I by 3. UCD is equal to minus half into I by 3 divided by 2I by 3. So this is equal to minus 1 by 4. So these are the rotation factors. Then find out what is the piston moment at joints. So as you know, so at the joint B there are three members meet. So BA, BE dash and BC. So what is the piston moment at the end of the member? So the summation of these three piston moment, that is equal to the piston moment of the joint B. Similarly, at joint C there are two members meet. Here you find out the piston moment of the joint C, that is MFC is equal to MFCB plus MFCD. So here you know the sum of piston moment at B, MFB is equal to MFBA plus MFBC plus MFB dash. So here you know MFBA and MFBC, both the piston moment 0, and MFBA is equal to minus 40. So 0 minus 40 is equal to minus 40 kilonewton meter. Similarly, the sum of piston moment at C, MFC is equal to MFCB plus MFCD dash. So MFCB is equal to 0 and MFCD is equal to minus 60. So this MFC is equal to 0 minus 60 is equal to minus 60 kilonewton meter. So this is the piston moment at joint B and C. Then find out the rotation moments by using the piston moments and the rotation factor, and find out what is the rotation moments. By using this type of tabular form, you can find out the rotation moments. So this is the piston A, and this is the joint B, and this is the joint C, and this is the piston at the midpoint of the beam D dash, and this is the piston at the midpoint of the beam, that is E dash. At the joint C, make two rectangular block, and at joint B, make two rectangular block. In small rectangular block, write what is the piston moment of the joint C, and here in small rectangular block, write what is the piston moment of the joint B. And you know what is the piston moment MFCD. Just above this line, write the MFCD value, and at the piston moment at the midpoint, this is your 0. Similarly, on this member B dash, here you write MFB dash, MFB minus 40 above this line, and MFE dash B, so this is 0 as the axis is passing through the midpoint of the B. So these are the piston moments, just write above the line, and this is the piston moment of the joint C. And in the trapezoidal box, so write the rotation factor, and the rotation factor UBA write in this trapezoidal box, and the rotation factor UBE write in this trapezoidal box, and the rotation factor UBC write in this trapezoidal box. Similarly, the rotation factor UCB write in this trapezoidal box, and UCD write in this trapezoidal box. So these are the rotation factor, write in corresponding box. Then find out the near end rotation moment. So these are the near end rotation moment. In first cycle this is the value, and second cycle this is the value, third cycle this is the value, and fourth cycle this is the value. So after iterating the fourth cycle, similarly at the joint C, this is the first cycle value, this is second cycle value, this is third cycle value, and this is fourth cycle value. Similarly at joint B, so this is first cycle value, and this is second cycle value, and this is third cycle value, and this is fourth cycle value. As you know, when the difference between the two cycle is less, then you stop the iterating process, and the final cycle reading is you have to take the rotation moment of the end of the members. Here at the end D dash is fixed, so here you take the rotation moment 0, and at the end E dash is fixed, here you take the rotation moment 0 just to write below the line, and at the support A, due to the fixed end, the rotation moment is equal to 0. Then find out the near end rotation moment. In first cycle, first you go to the joint C and find out what is the near end rotation moment. The axis is passing through the midpoint, so this is the fixed end, so here the rotation moment is 0. In first cycle, assume the far end rotation moment m dash bc, that is equal to 0, and find out what is the near end rotation moment. So the near end rotation moment, that is equal to m dash cb. Here you find out the m dash cb and m dash cd. So m dash cb, this is the value, and m dash cd, this is the value, near end rotation moment. So m dash cb is equal to ucb into mfc plus summation of m dash bc. So you know ucb, this is the ucb value, minus 1 by 4, and mfc you know minus 60, and the summation of m dash bc, this is the sum of the far end rotation moment you have to consider. So in first cycle, so this side you have to assume the far end rotation moment is 0, and at the end d dash is fixed, the far end rotation moment this side is also 0. So take 0 plus 0. So m dash cb is equal to plus 15 kilonewton meter. Similarly find out m dash cd, that is equal to ucd into mfc plus m dash bc. So m dash cd is equal to minus 1 by 4 minus 60 plus 0 plus 0. So this is also equal to plus 15 kilonewton meter. So put this value 15, and here also put m dash cd 15 and m dash cb, this is also 15. Then you go to the joint B. So in joint B, in first cycle, find out the rotation moment, this moment. As you know, the end A is fixed, the rotation moment at the end A is 0, and the end E dash is also fixed, the rotation moment here is also 0, and this side you got the rotation moment 15. This side you got the rotation moment 15. So when you are considering the joint B, so you have to take this as a far end rotation moment for joint B, and find out what is the near end rotation moment m dash ba, m dash b, and m dash bc. M dash ba is equal to uba into mfb plus summation of m dash ab. So mfb, this is the fixed end moment of the joint B, and this is the far end rotation moment of the member ba. Similarly m dash bc is equal to ubc mfb plus summation of m dash bc, and m dash be is equal to ub into mfb plus summation of m dash be. So here you know the rotation factor, this is minus 1 by 6 uba, and ub minus 1 by 6, and ubc minus 1 by 6, and the rotation moment 0 0, and this side you take 15, and the fixed end moment of the joint B, here you take minus 40. So minus 1 by 6 into minus 40 plus 15 plus 0 plus 0. So this is equal to 4.17 kilonewton meter. This is equal to 4.17 kilonewton meter. M dash BA 4.17 kilonewton meter. M dash BC 4.17 kilonewton meter. m dash B 4.17 kilonewton meter. Then you put the value here, m dash BA here, and m dash B here 4.17, and m dash BC here 4.17. Now first cycle is over. Then you go for the second cycle and find out the second cycle reading. First at the joint C, then find out the value at the joint B. The second cycle reading 13.96 at joint C, and at joint B 4.34, 4.34 and 4.34. This is the second cycle reading. When you are considering the joint C, the end D dash is fixed, so here the rotation moment is 0, and this side the far end rotation moment you have to consider, this is 4.17. What is the moment you got at joint B? So this moment you have to consider far end rotation moment for the joint C. So this side you take 0, this side 4.17, and the rotation factor -1/4, and the fixed end moment of the joint C, this is -60. Then find out m dash CB and m dash CD. So m dash CB is equal to UCB into MFC plus summation of m dash BC, and you know UCB is equal to -1/4, MFC -60, and here you have to take the far end rotation moment, one side 4.17, you got what is in the first cycle, and the other end you take 0 as the axis is passing through the midpoint, so you are considering that point as a fixed end 0. Here m dash CB is equal to 13.96 kilonewton meter. Similarly m dash CD is equal to -1/4 -60 plus 4.17 plus 0, so this is also 13.96 kilonewton meter. So you put here the 13.96 and 13.96. Then you go to the joint B. So at joint B, so find out the second cycle value, that is m dash BA, m dash BE and m dash BC. When you are considering the joint B, here you have to take the rotation moment at the end A 0 and at the end E dash 0. This side you have to take the rotation moment 13.96. So find out m dash BA, m dash BE dash and m dash BC dash. So in second cycle at joint B, m dash BA is equal to UBA MFB plus summation of m dash AB. M dash BC is equal to UBC into MFB plus summation of m dash CB. Then m dash B is equal to UB into MFB plus summation of m dash EB. You know the rotation factor -1/6 and the fixed end moment of the joint B -40, and this is the rotation moment of the far end. So one side the rotation moment you got at the joint C in second cycle, that rotation moment you have to take the far end rotation moment for joint B. Other two end, due to the fixed end, take the rotation moment that is equal to 0. So here m dash BA is equal to 4.34, m dash BC is equal to 4.34 and m dash B is equal to 4.34 kilonewton meter. Then write this rotation moment 4.34, 4.34 and 4.34. Then the second cycle is over. Similarly, you can carry out the iteration process and find out what is the rotation moment in the third cycle. So in third cycle, the rotation moment at the joint C, m dash CB is equal to 13.92 and m dash CD is equal to 13.92. Similarly, find out what is the rotation moment at joint B. For third cycle, the rotation moment m dash BA is equal to 4.35, m dash B is equal to 4.35 and m dash BC is equal to 4.35. Then again you go for the fourth cycle and you go to the joint C. So at joint C, find out the rotation moment m dash CB and m dash CD. So in fourth cycle, the rotation moment m dash CB you got 13.91 and m dash CD you got 13.91. So put this is the fourth cycle value. Similarly at joint B, rotation moment m dash BA 4.35, m dash BE 4.35, m dash BC 4.35. These are the final value So then you compare the third and fourth cycle. So there is the very small difference, there is 0. So here the difference is 0, and here there is very less difference, 13.9 to 13.91, 13.9 to 13.91. Stop the iterative process, and final value that you take the rotation moment for the end of the members. This is the third cycle value, 4.35, 4.35, 4.35. This is 13.9 to 13.92 kilonewton meter, and this is 4.35, 4.35, 4.35. Then this is the fourth cycle value, m dash cb 13.91 kilonewton meter, m dash cd 13.91 kilonewton meter, and m dash ba 4.35 kilonewton meter, m dash bc 4.35 kilonewton meter, and m dash be 4.35 kilonewton meter. So this is the rotational moment, m dash ab 0, m dash ba 4.35, m dash bc 4.35, m dash be 4.35, m dash cb 13.91, and m dash cd dash 13.91 kilonewton meter. These are the rotation moments, and these are the piston moments. Already you know at the beginning, mfcd minus 60 kilonewton meter, mfdc plus 60 kilonewton meter, mfb minus 40, mfeb plus 40, and for vertical member the piston moments are 0. So by using the rotation moment and the piston moment, so find out the final moments. So by using this formula, MAB is equal to the piston moment AB plus twice the near end rotation moment plus once the far end rotation moment. That is MAB is equal to MFAB plus twice M dash AB plus M dash BA. Similarly, MBA is equal to MFBA plus twice M dash BA plus M dash AB. So by using this formula, find out the final moment. So the final moment MAB is equal to 0 plus 0 plus 4.35, that is equal to 4.35 kilonewton meter. Because you know the piston moment AB, this is 0 and 2 M dash AB. So M dash AB is also 0 and M dash BA 4.35. 0 plus 4.35 is equal to 4.35 kilonewton meter. Similarly, find out MBA is equal to MFBA plus twice M dash BA plus M dash AB. So MFBA, this is also 0 and twice M dash BA. So twice into 4.35 and M dash AB, this is 0. MBA is equal to 0 plus 2 into 4.35, that is equal to 8.70 kilonewton meter. Similarly, find out MB. So MB is equal to MFB plus twice M dash B plus M dash EB. MFB minus 40, MF minus 40 and twice M dash B 4.35, 2 into 4.35 and M dash EB, that is equal to 0 due to the fixed end. Then this is equal to minus 31.30 kilonewton meter. Similarly, find out MBC. So 0 plus 2 into 4.35 plus 13.91. So this is equal to 22.61 kilonewton meter. Then MCB is equal to 0 plus 2 into 13.91 plus 4.35 is equal to plus 32.17 kilonewton meter, and MCD is equal to minus 60 plus 2 into 13.91 plus 0. So this is equal to minus 32.18 kilonewton meter. So then you check at the joint B and C, the sum of the moment is coming 0 or not. Here you check at the joint B. So there are 3 members meet, MBA, MB, MBC. So take the summation of these 3, that should come 0. And at joint C also there are 2 members meet, C. Sum of the moment should also come 0. But here due to the calculation error, so here we got 32.17 and 32.18. So take the same value 32.17 here. And here also you take 70, 30 and this is 61. So here also just you remove the error and take the summation is equal to 0. This is the final moment, 1/2 portion of the beam. This is the final moment of the substitute frame. Here you got the final moment of the left half portion. This is the portion. So for the left half moment, here you got this is MAB is equal to 4.35 kilonewton meter, MBA is equal to 8.70 kilonewton meter, and MBC is equal to 22.61 kilonewton meter, MCB 32.17 kilonewton meter, and MB is equal to minus 31.30 kilonewton meter, and MCB is equal to minus 32.18 kilonewton meter. Here you got the final moment of the left half substitute member, and the right half take the same value but in opposite sense. Here you got minus 32.18 MCD, so MDC you take 32.18 kilonewton meter, and here you got MB is equal to minus 31.30, and this side you take MEB is equal to 31.30 kilonewton meter. Take the same value but in opposite sense. Similarly, MAB, here you got 4.35 kilonewton meter, and this side MFE you take minus 4.35 kilonewton meter, and MBA 8.70, and MEF you take minus 8.70 kilonewton meter, and MBC 22.61, and here you take MED minus 22.61, and MCB 32.17, and here you take MD minus 32.17. So these are the right half moment, and these are the left half moment. So the right half moment you take the same value but in opposite sense. So this is the right half, this is the left half moment, and this is the right half moment, and this is the final moment of the full frame. Then after knowing the final moment, then give the direction of the moment, then you can draw the final bending moment diagram. So this is the direction of the moment. So as you know, the clockwise moment, that is positive, and the anti-clockwise moment, that is negative. So here you see these are the value, this is the positive value. So for this positive value, so draw the direction of the moment, that is clockwise, this is clockwise, this is clockwise, and here you know this is the negative value, and for the negative moment, so draw the direction of the moment, that is anti-clockwise, this is anti-clockwise. Similarly, so just to complete all the direction of the moments, then after you can draw the final bending moment diagram. Here you see the arrow mark is towards inside, so here the tension is inner side, so take here this side 4.35, and here the arrow mark outside, so here you take 8.70, then join these 2 points, this one 8.7 and 4.35, join these 2 points. Similarly, here you see for this vertical member the arrow mark inside, and for this vertical member this is outside, and here you take inside 22.61, and here you take outside 32.17, 22.17, join these 2 points, and this is the bending moment diagram of this vertical member. Similarly, this side also for vertical member, this is inside, this is outside, take 4.35 inside, and here you take outside 8.7 and join these 2 points. Similarly, here you take 22.61 inside, and here you take 32.17 outside and join these 2 points, and this is the bending moment diagram for the vertical member. And for the horizontal member, so here you know 31.30, and this side also 31.30, so take here 31.30, and join these 2 points. So this is the negative bending moment diagram. Similarly, here 32.18, and this is also 32.18. So here you take 32.17 because this is 32.17. So this value also you take 32.17. So draw here 32.17, 32.17, and this is the negative bending moment diagram due to the support moment. Due to the UTL present on the horizontal member CD, you can draw the free bending moment diagram. So the free bending moment diagram, that is the parabolic, and you can find out the maximum free bending moment value, that is W L square by 8. Here the load is present on this horizontal member CD 30 kilonewton by meter, and the length is 6 meter. So W L square by 8, that is 30 into 6 square by 8. So the moment, the free moment or the positive moment, that is 90 at the midpoint of the top horizontal member, and at the mid horizontal member here, so there is present two concentrated load. So due to these two concentrated load, draw the free bending moment diagram. So here this is the free bending moment diagram, trapezoidal shape. Then so this is the positive moment, and this is also the positive moment. So here this portion is cancel each other, and here also this portion is cancel each other. Then this is the positive, and this is also the positive, this is negative, this is also positive, and this is negative, this is negative, this is positive, this is negative, this is negative, positive, negative, this is also positive, this is negative, this is positive, and this is the final bending moment diagram of the symmetrical frame when the line of axis which is passing through the midpoint of the beam. Now all are clear how to analyze the frame when the line of symmetry which is passing through the midpoint of the beam.